We're going to be looking at is we're going to look at how to draw, how to analyze a position time graph, but also how we're going to write an equation for that. Now, this is going to be review from your Algebra 1 math class, but what we're going to be doing is taking the information from the graph, building on what you already know from algebra, and then putting physics language onto it. Because what we like about algebra is algebra and all math equations are a nice generic format, but we always want to make it specific to the data that we have. So if you take a look at the sheet that's in front of you, the purpose of our line of best fit is to generalize data. Now, once we generalize the data, then what we're able to do is see what kind of mathematical trend there is. So there could be lines of best fit to generalize the data, and there could be curves of best fit. But the point is we want to generalize it to find a math trend, a mathematical trend. Now, a lot of people think that linear is obviously one mathematical trend. You could have curves of best fit. So those curves of best fit could be quadratic, they could be exponential, they could be logarithmic, they could be inverse. There's lots of different mathematical trends. Now, if I take a look at the data that's been given here with the x's as our point, if we're going to describe the motion on the graph, you can tell that the object is starting at 2 meters. And I can tell that simply by going back and taking a look at where that line of best fit would go to. Second thing that I know is that it goes in a positive direction. I know it's going a positive direction because there's a positive slope. And then lastly, what I want to do is I want to go ahead and find what the velocity of the object is. In order for me to determine what the velocity of the object is, I first have to go ahead and draw my line of best fit in. Now, when you draw a line of best fit in this case, what you're trying to do is you want to try your best to go through as many data points as possible. Okay, that's what your plan is. That's what you want to do. If you can't go through all the data points, then what you've got to do is you have to try to split the difference, which we've talked about. So let me get my tool out to draw my line in, and I'm going to do my very best, starting it right about 2. And I'm going to draw in my line of best fit as best as I can, if my tools are going to work here. All right. Okay, for some reason my tools are not working, so I'm just going to go ahead and do a free draw of my line of best fit. And there's about as straight a line as I can get. Okay, ideally you're using a ruler to do this. Now you also know to find the velocity you have to select 2 points that are on your line of best fit. Those are the 2 I've selected. I'm going to shade in my rise and shade in my run. Now you always want to be careful when you're doing this that you are not just counting boxes, but you're going by the scale. So if you look, 1, 2, 3, 4, 5, I've got a rise of 6 boxes and each box is worth 1. Going across, I have my scale is also by ones and it's 7 seconds. So my velocity I ride is a fraction. 6 meters divided by 7 seconds. In other words, rise over run. And you should get 0.86 meters per second. So that tells me for every second, my object goes 0.86 meters. Now, if you think about what you have in math class, when you write a linear relationship, you always start with the nice generic equation y equals mx plus b. Now, if we go back and kind of recap what these variables are, the y stands for what's along the y-axis, the m stands for the slope, the x stands for what's on the x-axis, and the b stands for the y-intercept. So if you were in math class, you would then replace 2 of the values. You would replace the m with the slope of the line, and you would replace the b with the y-intercept. So you would rewrite this equation in math class. The slope is 0.86, and then x comes down. And then our y-intercept is 2, and that's how you would write it in math. Now, what we want to do instead is we want to transition that to physics language, because y's, x's, m's, and b's are just generic for what they mean. And I'm going to start with the b first. So I'm going to work my way backwards. Now, we already know what the b represented. It represented the y-intercept, but it also represents the starting position. So I'm going to start back at the back part of the equation, and I'm going to say the b is my xi. So xi is the same thing as b. Now then I look across the next one and I see the x. Now x represents what's on the x-axis. In this case, it's our time. Now we know the symbol that we use for time. We actually call that delta t, or change in time. So time has crossed my x-axis, so therefore that's what I'm putting. Now my m is my slope of my line, and that's the number I already know, which is 0.86. Now if you want to put parentheses around it, you're welcome to do that. Then we take all of that and we put that equal to what's on the y-axis. Now, the y-axis, remember, is up here, and we know that position is on the y-axis. Now, we know there are two kinds of positions we've talked about in this class. We've talked about xf and we've talked about xi. So if you look at this equation, xi has already been used. So therefore, xf is what you can solve for. Now, here's the beauty of this equation. This equation you can do calculations with. So say you don't have a graph, but you have a mathematical pattern, you've written an equation. Now you can figure out what happened, where this object is going to be after 10 seconds if you look at the graph, after 6 seconds if you look at the graph, after 2 seconds if you look at the graph. However, say you want to calculate where it's going to be after 100 seconds. Well, that's not on the graph, so therefore I can calculate it. And that would give me my final position after that time. Now, once again, I'll let you do the bottom part. You can find the slope of this line. You can write your equation the math way. You can write your equation the physics way. And basically what we end up with is one big idea at the very bottom. And the big idea is that if I have a linear relationship on a position versus time graph, and that only applies when there's constant velocity. So when there is a constant velocity, when there's a constant velocity, we will have a linear position time graph. And it will follow a mathematical pattern of y equals mx plus b. However, we don't use y's, m's, x's, and b's. We're going to make this specific to the type of data that we do have. And then we can rewrite it using our physics variables. Instead of y equals, it's xf equals. Instead of m, we know that m stands for the slope of the line, which represents the velocity in this case. So instead of saying m, we're going to call it what it is, which is velocity. Across the x-axis is time. And finally, our b represents our y-intercept. Our y-intercept on this type of graph is xi, or starting position. Now, when you look at this, you can do calculations very easily. So, for example, if I did one simple calculation here, if I wanted to find what my xf was, and my velocity was 3 meters per second, my object moved for 3 seconds, and my starting position was 1 meter, then I just do the math. I know that 3 times 3 is 9, so that's easy. The math is easy. The units will cancel, leaving meters behind, plus 1 meter. So this object will travel a total of 10 meters. Now, I'm sorry, this object will be at position 10 meters. Okay, so if I were going to draw a motion diagram of what I just calculated, my object starts at 1 meter. My object is moving a positive direction at 3 meters per second. And my object moves for a total of 3 seconds. So the position I should end up at will be 10 meters. However, the change in position for the object is going to be 9 meters because xf minus xi gives me 9. Now, try the practice.